Good afternoon. Welcome to everybody for this Data Drives 20 seminar on data science applications. It's a seminar on data science applications for data-driven decision making. DataSEARCH is a multidisciplinary research center for University of Moratuwa, and the reason behind organizing this seminar is to promote data-driven decision making, and we are trying to get the academics, industry, and others who are involved in data science to collaborate and promote the use of data science for decision making. We are privileged to have Data Analytics and Cognition Lab from La Trobe University to co-sponsor this, and also we have 4 distinguished presenters from across the globe who are waiting to present. We would encourage you to ask, if you have any questions, to ask using the Zoom Q&A, because during the seminar, we will keep all the participants on mute, and we will try our best to make sure that we get your questions answered. Let me welcome our first speaker, Dr. Su. Dr. Su Nguyen from La Trobe. He's a fellow, a research fellow and algorithms lead at the Center for Data Analytics and Cognition, La Trobe University, Australia. He received his PhD in Artificial Intelligence and Data Analytics from Victoria University, Wellington. His expertise include evolutionary computation, simulation, optimization, automated algorithm design, interfaces of AI and operations research, and the applications in logistics, energy, transportation. His current research focuses on novel people-centric artificial intelligence to solve dynamic and uncertain planning tasks, to enable human-AI collaboration with the combining creativity of evolutionary computation and computation to maximize the power of machine learning in algorithms. He was the chair IEEE Task Force on Evolutionary Scheduling and Combinatorial Optimizations, and member of the IEEE CIS Data Mining and Big Data Technical Committee. He has delivered a lot of technical tutorials at prestigious events, and he has a lot of publication in top peer-reviewed journals. Let me introduce Dr. Su to continue, or actually start this seminar, where he will be talking about evolvable problem solvers for big data era. Yeah, Dr. Su, you can take over from here.
Thank you, Dr. Shan. Can you hear me clear?
Yes, we can hear you.
Yeah. Let me share the screen. Just want to check if everyone can see the slides.
Yes.
All right. Okay. Let me. Can I start now, Dr. Shan?
Yes, you can go ahead.
Okay, thank you. Good afternoon, everyone from this is from Sri Lanka. So this is a bit like evenings in Melbourne. My name is Nguyen. For this talk, I'm going to discuss evolvable problem solvers for big data eras. A little introduction about where I come from. I'm from La Trobe University. This is a research university located in the north part of Melbourne. This is our campus is the largest campus in Australia, largest city campus in Australia, and the university put a strong focus on research that bring positive social impact. And I'm with Centers for Data Analytics and Cognition, which is a collection of computer scientists and AI researchers. We try to bring in disruptive technologies, AIs, to to build new innovations and add new business values. So the focus of this talk is about problem solving, but before I go into the key topics, I would like to review what happened with problem solving in the past. So my background is where I'm doing my bachelor's in industrial engineering. So I have a tendency to use applications within production and logistics domains. So I remember in my first internship jobs is actually in the factories, and usually we approach problems is usually driven by an orders from the boss. Let's say we try to improve the production throughput. Let's try to production speed or production lines or factory plant. And with that instructions, then we go try to collect more data. We try to preview the process, try to understand the process. And this is a lengthy process because most of the data at that time is like papers and is not entirely digitalized. And then we're gonna actually it's like varies by a lot of documents, and that requires us to entry into the computers before we can do some analysis. But usually finally we got some things interesting, something that present an opportunities for improvement. Then the next step is, okay, you already identify the problems and opportunities, then can you provide a solution for that? Then we need to get back to our team and try to figure out what is the best way to utilize these opportunities. And it's another lengthy process, and with some luck, we may end up with some solution. But if the entire process is going to be too long, then we sometimes end up with the situation where the solution become obsolete and cannot be used. So because it's because I come from engineering, so I like to use flowcharts to visualize the complex system and try to identify problems. And with this flow, then there's two big bottlenecks. First one is with the data analysis, and the second one is with the solution development. Now is actually a little bit better. We have a lot of new technologies that allow us to collect a large amount of data from different sources. We have our industrial IoT that collects every activities within the factories. If you talk about social media, then you have a lot of information contents you can collect from social medias. Or from transportation, then a lot of sensors and cameras that allow us to monitor closely the traffic activities. We also have a big help from advanced analytics technologies that allow us to quickly generate insights and present in a very nice format that allow us to explore opportunities and also identify problems. So moving from data into some interesting insights or opportunities actually is much faster now. But then we still have problems with, yes, we have opportunities, but it's not quite easy to move that into solution. It's required an extra step, and for this solution development step is still not quite convenient. And another problem right here is because of the advance in big data analytics, then actually we're going to get a lot more insights and opportunities. And this requires quite big bottlenecks at the solution development step. So there's different ways to develop solutions. In this talk, I mainly focus on data-driven optimization. What is simply is like we try to formulate the problems as computational or mathematical problems using computational or mathematical models. and try to develop a solution using numerical approach or analytical approach. So the methodology is for data-driven optimization is pretty simple. So we start with these problems. We try to conceptualize the problems so that we can have high-level understanding of what's happening. And then we try to model it using some scientific models. It can be mathematical modeling. So we can model it using network. You can use computers simulation to model it. And then we're going to rely on some solver to identify a solution. There's going to be quite a lot of available modeling language and solvers, both commercials or open source, and it's keep improving over time. But it's the abilities to model the problem doesn't mean that you can actually solve the problems, because some problems actually is quite challenging and require a lot of computational time to solve it. And unfortunately, the solving piece is quite problem specific. You need to have some domain knowledge in order to efficiently solve the problems that you model. And sometimes it's quite time consuming to find good solution methods, unfortunately. Just in this slide, I just try to give a very brief reviews of solution methods. There in no way a comprehensive reviews, but just to give you a flavor of what things might look like. So for solution methods, then one is supposed to be heuristics, or what we consider as rule of thumbs, in which we, based on experience or what you understand about systems, and that you may up with easy, very scalable solution that can make decision in a fraction of a second. Then for some complex application where you can use mathematical models to formulate your problems, then is quite a lot of available optimization algorithms that you can use to reach optimal solution. So in that case, you can just simply select from a set of optimization algorithm to apply. And in the worst scenarios when we cannot find any good solution methods, we have to develop new algorithms. So after we come up with some solution methods, we're going to apply it into some decision-making situation. Decision-making situation most is come from the data that represent environment in which those solution methods going to be applied, or where the solution going to be implemented, executed. And after you try on some decision-making situation, you evaluate the qualities of your solution. And then you go back and revise your solution methods. And this step usually is going to take quite a number of iterations up to the point that you're happy with your solution methods. And in the past, we're going to see that a lot of PhD study actually focus on these loops and try to come up with a better, more efficient solution methods. But at the end, what we want, the whole process I present here actually is what we try to learn from the experience when we try to solve the problems. And the goal is we want to obtain optimal, better solution. Hopefully, it's going to be actually an optimal solution. If not, if is it possible. And we also try to be more efficient, because certain application is quite very quick decision. It's in a few seconds rather than you provide solution in hours. We want to achieve better generalization. We want our solution methods can be applied to situations that are sometimes not presented in the data, but it still can solve them. We try to identify robust solution that kind of adapt well with these uncertainties. And also, we want to interpret decisions. One of those, if you are in data science, in the data science, then all of those actually is quite similar to a job of a data scientist, or what AI and machine learnings have been used for, learn from experience. What happened at the moment is that there's rising interest in applying machine learning to optimization. So it says instead of focusing on cognitive tasks like image classification, detect anomalies from videos, or so like from IoT data, now there's a branch of research in machine learning that really focus on how to realize the power, the usefulness of machine learning in optimization. Machine learning algorithms have been applied to automatically design heuristics. Given that you have in past data of the situation in which you understand what is the best action that you can take, you can use that. You can use machine learning algorithms to learn to make those decisions automatically. And in the case that you already have a group of optimization algorithms, you can apply machine learning algorithms to select the best algorithms, optimization algorithms, based on the patterns that we extract from the situations. We can also use machine learning algorithms to configure optimization algorithms, or even use that to automatically design optimization search algorithms from scratch by combines all the small components from the bus algorithms. We find smart way to put them together to create a specialized solution method for the problem interest. In the last few years, we also see deep neural network have been applied to learn representation of the optimization problems. So instead of you have to build yourself to be an expert to understand the problem and try to find the best way to solve it. Now you can actually learn it from scratch. And there is some studies looking at end-to-end learnings for how optimization problems, where you can go back to the low-level representation of problems. This can be a graph, it can be a network, and try to learn all the patterns in there and attach them into the decision-making layers. And currently, this direction of research have moved through some advanced topics. Now we talk about multitask learning, in which we try to use machine learning to learn different decisions within a complex system. For example, in production, you have to work with the routing decision where you will need to allocate jobs to machines. You need to look at scheduling decision in which you try to decide when to start a job. Those are interdependent decisions, and this need to be learned at the same time. You're also interested in transfer learnings. For example, if we try to optimize operation in container terminals, for example, in Australia, if we find a nice solution methods to optimize operation in the terminals in the port of Brisbane, can those knowledge transfer to the operation of port in Melbourne? This is currently a hot topic. We also interested in multi-criteria decision making, because in most business problem, we're going to look at more than one objective or one criteria. We usually look at multiple criteria. For example, in portfolio optimization, we look at risk and return. This topic is not new in optimization, but this has not quite been explored when machine learning is used for optimization. And finally is the application of adversarial machine learning into optimization in order to help identify the situation in which the solution methods or the optimization may not work. This is equivalent to worst case analysis in algorithm designs, but we're using machine learning to identify the situation in which the algorithms may have trouble This is needed in order for us to come up with a backup plan, so that our system gonna run smoothly, and we can anticipate what may happen, when it may happen, to respond accordingly. So this is just give feelings of what problem solving might look like in the past and right now. But for the futures, this is maybe a lot more interesting, because we slowly sees on a small piece of technologies being bring together, and we can expect great things in the future. I try to redraw the flowchart that I have shown, the complex flowchart that I showed before. Try to bring in all this existing technologies. Now we have big data, advanced analytics that provides with insights. But with that, then decision makers or the users, we can make a problem statement. This is something from that where we understand what's happening. We can make a problem statement. We can define business problems. And then with the insights and problem statements, we can use some advanced natural processing technologies and use them to automatically transform the problem statements and inside data into computational models automatically. And those going to transfer to an evolvable problem solver, which can learn from experience. The more is engaged and try to work with this situation, the better it's going to be. And when they come up with acceptable solution methods, it's going to bring it back to the users. So this is the futures. One of the scenarios that I think that the future might look like, where you bring in all the technologies together. To conclude, for this talk, I just try to provide an overview of what have been happening in my related research. And I'm really passionate about Evolvable problem solver, and I think it's going to be the next stage of AI application, especially since I believe there's going to be innovative application of AI machine learnings that responds to the big data's errors. And this is going to be exciting and open research areas. It's not quite well explored, so there's going to be a lot of opportunities. And this is where you can bring on the multidisciplinary knowledge and expertise together to come up with a novel solution. And it also can lead to real impacts, because what you're looking at the moment is that machine learnings help automation to make decision, to lead to optimal decision. So when you go to automated decision making step, this is where you can actually make a real impact. So thank you. This is basically the end of my talk.
Thanks, Dr. Su. We are waiting. If you have any questions, you may ask on the Zoom Q&A. Yeah, even on the chat, that's okay.
So Dr. Sudi did a wonderful presentation. Is that what it means to not to have questions?
You can ask.
I'm sorry, is that a question?
No, no, no. Yeah, we are waiting on the Q&A. Yeah, there's one question. Yeah, Dr. Su, there's a question. What is a evolvable problem solver? You can see the questions.
All right.
Yeah, maybe you can
yes,
check.
I guess. Yeah. So my definition of evolvable problem solvers are the solvers that can actually evolve and adapt to decision-making situation. For examples, if you are looking at the application in the manufacturing, where you try to produce, let's say, smartphones, you have assembly lines to produce smartphones, and you try to allocate the best manufacturing resources into your assembly lines, try to adjust the speed and also the component that's going to be processed in each station. So those are optimization problems, and you need a problem solver to solve it. But imagine that you try to produce iPhone 10, and now it's going to iPhone 12.